Thanks, Jodie. It's my very great pleasure to introduce this plenary on mathematical problem solving. As Boris notes in his wonderful paper, research on problem solving and its role in mathematics education has been the focus of a very significant amount of research over many, many years. Indeed, at my very first PME, wait for it, PME7 in 1984, this topic was very much at the forefront of deliberations. At the time, I just commenced my PhD on the role of metacognition in children's mathematical problem solving, so I'm very much looking forward to this opportunity to rethink this very important aspect of mathematics education. Boris comes to us as a multi-award-winning teacher, scholar and researcher. He completed his Master of Science in Mathematics at Leeds State University in 1991 before working for 8 years as a teacher in Ukraine. In 1998, he repatriated or moved back to Israel, where in 2004 he completed his PhD on junior high school students' heuristic behaviours in mathematical problem solving. He did this at the Technigon, the Israel Institute of Technology. In 2006, after a 2-year postdoc at the University of California, San Diego, he returned to the Technion as a faculty member. In 2017, Boris moved to the Weizmann Institute of Science and is currently there a full professor and head of mathematics group in the Department of Science Teaching. Boris is well known for his work as a journal board member, an editor and reviewer. He's an associate editor of the Journal of Mathematical Behaviour, a founding editor of the Implementation and Replication Studies in Mathematics Education, and a guest editor of the special issue of ZDM on the implementation of mathematics education research. In addition to this, he represents Israel on the International Commission on Mathematics Instruction. His research is focused on teaching and learning mathematics through problem solving and problem posing in the middle years through to university. He is particularly interested in the mechanism of problem solving and problem posing in choice affluent learning environments and in the possibilities afforded by teacher-researcher partnerships. Boris has won multiple teaching awards along with other awards for his research and his contributions as a reviewer. In 1989, Boris married Olga, a quality assurance engineer. They have 3 children, Michael, Julia and Dahlia. Boris likes jogging and playing tennis, and he enjoys listening to audiobooks in both Russian and Ukrainian while driving from Haifa, where he lives, to Rehovot, where he works. Let's give him a warm welcome to give his talk on the secret life of mathematics.
Kia ora, good morning, dobroho ranku, shalom. This is a brief summary of my movement around the globe during my life. I must say that during my last probably 5 PME conferences, it so happened that I presented in the first part of the conference. Thank you very much to everybody who made it until today, and I can confess that the experience of having the lecture during the last day is very different from the experience of having the lecture at the beginning. So, the secret life of mathematical problem through the lens of research practice partnerships. What it is about. Actually, during the next 55 minutes, I'm going to do 2 things. I'm going to introduce a metaphor and argue that problems can be usefully considered as discursive creatures, have their own life. These lives have secrets, and sometimes it is in our power and wish to reveal some of them. And after that, I will make a claim. I will say that the life of these creatures is very fragile, and in order to keep them alive, nobody is powerful enough, and we really need to enter seriously into the business of research partnerships. Well, but all these are nice words, and I am sure that some of you, in Wim's terms from the first day, you used newcomers and not very new newcomers, avoiding the word yes. So those who are around may ask by now, again, problem solving 2024. Indeed, in the history of PME, there have been 11 plenaries that were devoted to aspects of problem solving. beginning from the first one by Ephraim Fishben and finishing Patricio's plenary on problem solving last year in Haifa. During this big period of time, problem solving was considered from many different angles and perspectives. Just to give several examples, I'll mention that as early as in 1985, General Kilpatrick distinguished between 4 perspectives that then existed in the literature on problem solving. The first one, and probably the most popular until today, is a psychological. We have a goal, we have resources, and a direct goal is blocked somehow for a solver. Metaphors of hurdle, of obstacle, something like this. Mathematical perspective posits problems as constructions. Mathematics construct problems. Mathematics construct theories. Pedagogical, also known as teaching through problem solving, states that many things in mathematics, if not all of it, can be taught through problem solving, and problem solving can be a good vehicle for teaching, promoting important ideas other than just solve this kind of problem. And of course, social anthropological perspective that emphasizes the fact that problem solving does not occur in vacuum and occurs in interaction and transaction, and somehow problem is given and should be received in order to become a problem. To this end, probably the most famous distinction related to problem solving is the distinction problem versus exercise. I know that in different cultures, this word can have different meanings. For example, in Israel, in university courses, you have tutor who does exercises, even though by some other definitions it can be real problem solving. But Jeremy Kilpatrick distinguishes between those problems that require effort, the immediate road is blocked, and those that we know how to do it and have an algorithm. It can be a very complicated algorithm, but again, if I'm looking at the problem, understand it, and immediately know what I have to do, even if it will have an hour to finish it, it would be an exercise. I particularly like the quote that emphasizes the relative nature of what counts for a problem for different people. Researchers in mathematics education have long accepted the truth that a problem for you today may not be one for me today or for you tomorrow. In a way, it's optimistic. Something which was very difficult for me to solve yesterday, I can learn, and some problems can become exercises. Or, very recently, Alan Schoenfeld added to this problem solving versus exercise versus mystery. So far for the literature review, because this talk is not about history of research problem solving, just one more slide, because those who are newcomers and not very newcomers can probably read this slide as like a constant. For 50 or more years, there's some perceived gap between what we want about problem-solving extraction and what we have. And just to contrast, it is very desirable that students would perceive mathematics as a problem-solving activity, not only problem-solving, but including problem-solving, versus too often our students perceive mathematics as a collection of facts and procedures to be memorized. The next pair is, we want our students to develop positive attitude towards problem solving, but too often our students develop anxiety or even fear. Tell me what to do, not ask me to struggle. We want that many regular lessons for all students would be full with opportunities to be engaged in problem solving, and that this would not be restricted to only a special population like A student or students who prepare themselves for mathematical competitions. We want them for all. But in practice, many times our students in regular classes are given opportunity not to solve by themselves, but to follow explanations and use techniques. And of course, we want, it's mentioned in many, many documents that I will not quote here, that we want our students to develop problem-solving competences, but in fact, many times it is reported they develop competences of studentic. I learned this term from Peter Liljedahl some time ago. It's not his term, but he uses it, and I like this, like what the teachers do, they teach. What the students do, not necessarily learn. They student, which means that they develop and exercise habits of surviving in the system, not necessarily by learning something meaningful. So this is more or less, I think, could be put on the screen in the 7th PME, and it is quite relevant until today. But those who are newcomers to the community may probably not feel that problem solving as a research theme is so overwhelmingly well explored, and that I would not create an impression that it is very popular throughout the history. I would say that it develops in some kind of spirals. All this agenda that we need, everybody needs problem-solving skills and problem-solving as part of mathematics, actually came historically from big names in mathematics. And it was very natural to think how those who know how to solve problems do it. So it was repeated focus on expert problem solving. Then a wave of study about how to compare what experts and novices do in problem solving. So let's identify the gap. With this knowledge, let's experiment how can we, what we learn from expert, let's go to regular classes. At small scale, it sometimes works. We have reports by Frank Lester, for example. I'm referring now to that period of 18, that this experiment by many, many measures was very successful. In 2 classes participated. Then we want to upscale and immediately see that it's not this success is not that transferable, and much, much more things are involved in problem-solving teaching. So we make the things more complex, trying to account for what's going on in various classrooms. And sometimes we are frustrated. We have 5 years when problem solving is not popular. We don't have many papers on it. We don't have any presentations on it. But it's important, so the next cycle begins. So depending on when you began, when you came here to the PME community, you can feel that problem solving is here forever, or you can feel that it is quite a new theme. Of course, it's not for nothing. A real, serious accumulation of knowledge occurs as a result of this spiral development of the field. And by now, we know a lot about problem-solving processes. We know about characteristics of good problems, collaborative problem-solving in enhanced technology. We know about teacher knowledge needed in problem-solving, and more and more and more. But anyway, if we look at the literature in a bit more nuanced way, we will find there sentences that begin, we know something, but still don't know something else. I will not stay on this slide for a long time, but let's think, for example, about the second bullet. We know how to explain problem-solving failures and successes in some simple cases, but hardly know how to explain them in other cases. Let me give an example. Let's say that I observe a student, he is not successful, and I explain his lack of success in solving a particular problem because he did not remember a particular theorem that would help him. Or he just gave up too early. So this sort of things I can explain in terms of Alan Schoenfeld's, for example, problem-solving attributes. But now let's have 2 students from the same class. One of them knows the theorem, he invested a lot of time and did not succeed, and another one did succeed. So it's possible, and let's say that traditional simple vocabularies by which problem solving is described, has been described many years ago, would be not enough in order to explain the differences between these two close situations. To summarize, there are everlasting challenges that repeat themselves in some variations for many years about problem solving. It is an activity, problem solving as an activity for all is on the fringe of mathematics education practice in many countries. We still insufficiently understand the diversity of the role of a teacher when is supposed to teach problem solving way. And here are some basic tensions, like I am a teacher, I want my student to succeed. Why should I want them to struggle? And from here, all these cases when better explanation, better exploration, but no mean I cannot give my students more than 5 minutes of working independently and being in silence. This is not my job as a teacher. We all are familiar with this phenomenon, which is also described in the literature. Many tensions around this, and systematic lack of knowledge about what's going on in real classroom with mathematical tasks intended by their creators to be experienced as problems. We have problem books. Somebody wrote problem and intended that it would be experienced as a problem by one of the definitions I quoted. But is it happening? We don't know. Okay, we sometimes know, but not at large. Well, so far for introduction. But how a metaphor that I promised at the beginning can help to deal with all these challenges? Well, metaphor is a powerful thing. And to argue very briefly for metaphors, I, of course, turn to Lakoff and Johnson, who in their seminal Metaphors We Live By book explain metaphor as understanding and experiencing one kind of things in terms of another. It took me some time. I reread this definition for several times. Metaphor is understanding and experiencing one kind of things in terms of another. It was not intuitive for me, but I couldn't give any counter example for any metaphor that I'm familiar with. Furthermore, they argue that our conceptual system is largely metaphorical. That is, our ordinary understanding of the world is not based on some set of primitive physical concepts of propositions, but is rather metaphorical projections of the concept we use. They do not talk about mathematics, but if we need an example from mathematics education, first thing that came to my mind was a very well-known paper by Anna Start about two metaphors of learning. Metaphor of learning as acquisition and metaphor as learning as participation. And 3 bullets below are her argument about why it is important to talk about metaphors of learning and not just about learning. It really helps us to understand the nature of learning. Metaphors shape our educational practices, and in addition, sometimes they are helpful in order to reveal our underlying assumptions. Now I'm going to borrow this argument and play with something, with a new metaphor. Let us play with the following proposition. Mathematical tasks have lives in the same meaning as magic creatures from fables and fairy tales have tiles. Let me make my case very briefly. Magic creatures are born as discursive constructs. They exist on the pages of the books, but their lives depend on how readers of this book perceive this creature. The same for mathematical tasks. After all, they are discursive constructs that appear on the pages of textbooks and books, and their lives depend on how we attend or do not attend to these tasks. And if we think about discursive constructs and reality, both magic creatures and mathematical tasks can penetrate the experiential reality only via mediation of a real person. Somebody is supposed to read it, to solve it, to attend to it, to choose it. But what is interesting is that this influence is two-directional. We, of course, would agree that what we read and what we solve affect our lives. But would we agree that what we do with magic creatures and tasks affect their lives? Let me argue. My argument will be of the type that some mathematical creatures and some mathematical tasks are more alive than the others. And as an example, let me begin just from Tinkerbell from Peter Pan. We all probably remember an episode when it was in a play, not a movie, when she is sick and her existence or death depends on whether the children spectator say, yes, we believe that you exist. And if they don't believe that she exists, it's supposedly supposed to die. Another example that I found more recently is in a novel which is called Inkheart. A protagonist in this novel, Mortimer, has a special power. When he reads books aloud, creatures from this book appear in the real world. And with all this, let me now look at this discursive construct. It's so famous that it appears on bullets. It appears in Google search for 300,000 times. And it is, of course, because of its association with the Fermat last theorem. Let us consider this as an example for a moment. Fermat last theorem has a clear parent, Pierre Fermat, and a dramatic history, a dramatic story about how it was born. You know this, I have this short proof, but I have not enough space to write it, so on and so forth. It was very engaging for 200 years, for many, many years. I remember myself when a student in Ukraine in Lviv University, we had a faculty member, professor, who had a special assignment from the dean to respond to those amateur mathematicians who every year sent to the university their proof of Fermat's theory. Then the theorem was proved by Andrew Wiles in 1992, but does it mean that it is dead? No. Until today, there are attempts to find additional proofs and, of course, many generalizations. So the interest in this theorem is still alive, but probably it changed. It's not about is it true, quoting Keith Plenary. It's about something else, and it exists. It has existed as a problem, but for most of us, it exists like an artifact from somebody else's problem solving. It's not my problem, but it exists. So there's another mode of existence. Let's say with this example, I feel very comfortably to claim that, okay, Fermat's last theorem is still alive. But what about this example? Look at this pair of equations. The first one appears for 16,000 times on Google search, and another one for 8 times. And if you think that one of them has nice roots and another does not, it is not true. The first one has a root 4. We can try and guess and check it. And the second one has root -4. So with some time, it's not about technical niceness. For me, an explanation again comes from the history of mathematics, because the first one was used as a generic example in 16th century by Raphael Bombelli in his book Algebra. Many of us have heard about it because from that book we got legitimization of complex and negative numbers. He was the one who made sense of previous discoveries related to attempts to solve cubic equations. So it appears in the book of 16th century. Of course, it's reiterated many courses. And the second one, well, no special reason to think about it too much, only 8 times in Google search. And what about this pair? X squared minus 5x plus 6 equals 0, 80,000 times on Google search versus the second equation only 1 time on Google search. Again, both have roots, and here I attribute the difference probably to pedagogical convenience. I think that actually any teacher in the middle school at some point uses the first equations and it goes from one textbook to another, from one test to another. That's why so many citations. And the story of the second equation, I will tell you right now. I will try to apply a metaphor of a secret life of a problem to a particular task which is very close to my heart. It will be quite a long story, so it will take about 15 minutes to tell it. So please be patient, and please take several minutes to read this problem. It is called the miscoping task. Two students attempted to solve a quadratic equation. Although both students did the work correctly, the first miscopied the middle term and obtained solutions minus x and 1. The second student miscopied the constant term and obtained the solution 2 and 3. What is the right solution if there would not be miscopying mistake? I found this problem in a book by Lebochki Ruchnik, one of the problem books that I have in my office about 10 years ago. Later, I checked that variations of this task appear about 10 times of Google, so it's not very much alive, I would say. But if we think how to solve it, it's also not very much difficult. So we know the solutions, we know the equations. We have conditions about what was miscopied. So if one term was miscopied, the second one is right. And we quite quickly find out the roots of the correct equations. So it did not take too long for me to solve this problem. But something deeply surprised me in this situation. I was shocked, and I'll explain you why. As a schoolboy, I know that if I change a sign of the middle term, but keep the sign of the constant term, it is not a trouble in terms of the formula for solving quadratic equations. I mean that if the first equations had integer roots, the second was as well. But usually, if I change a sign of the second coefficient, not the first, it is a trouble. I not necessarily obtain an integer root, but radicals appear here. But here somehow, this task highlighted for me a pair of equations in which the constant term, the sign of it is changed. It is x squared plus minus 6 and plus 6, but both equations have integer roots. Just an observation. And I asked myself a very natural question. Are there more examples of this sort? And I couldn't find them. I spent some time trying to think about different combinations. So I understand that I cannot attack this problem immediately, and I formulated for me a question. So where this pair of equations can both have integer roots. And a little later, I formulated it in a more formal way and asked, find all, or at least some of the pairs of non-zero integers so that discriminants of the equations would be perfect squares. Well, double perfect square tasks, fancy name. But how can you approach this task? So what to do with it? It's number theory. You know that you can formulate something in number theory which looks very innocent, like last theorem of Fermat, and then it will appear very, very difficult. So after this trial and error period that I mentioned, I Googled it and searched it and didn't find anything useful. And then I did what I always do in my life. I asked my lifelong mentor and academic advisor, Professor Avi Berman from the Technion, a research mathematician. Avi not really was interested in talking about this problem. He gave me some advice that, truly speaking, I didn't understand. And okay, this communication has ended. So I should do something. What would Poya recommend me to do in this situation? No, the most trivial thing is to explore what we already know. We have a pair of equations that satisfy the conditions, so let's just think what's going on there. Well, discriminant of the first equation is 1, discriminant of the second equation is 49, which is nice. I have somehow numbers 7, 24, 25 pop up, and it's a Pythagorean triple. What to do with this observation, I still don't know, but it is nice, because if Pythagorean triples somehow appear in a problem, it opens horizons. There are many, many good conditions about it. But formally speaking, I have a system of 2 equations with 4 variables. I played with it and could not succeed, and next move, I'm telling you as if it was a linear story. I'm telling you a story about 2 weeks it took me. But at some point I said, let's simplify the problem and consider one of the a special case. The first discriminant is 1. Okay, here I can algebraically play with the system. And the second equation tells me actually something about coefficient C, because division by 8 is supposed to give me, after all, a whole number, which means that it's supposed to be odd number. I substitute and somehow trick-track, algebraic manipulations, and I have this result. And here I was looking at the internet, the closest picture that I could self-identify. So I was not in the bathroom. But it's really, I really feel enlightened. What happened? In my previous search on the internet, I of course looked at properties of Pythagorean triples, and I knew that this sort of Pythagorean triples has a special name and special properties. So it is called twin leg-leg triples, when 2 smaller legs are consecutive numbers. And there is a literature about this sort of things. Okay, the first triple of this sort we already know. It is 3, 4, 5. And if I do work backward with my equations from here, I just receive the pair of equations that I already know. So why it was so important for me? Because now I have tables filled out with leg triples. And the next one is 20, 25, 29. And if I do the work backward, I obtain this pair of equations that I mentioned before. What is the next one? Wow, it is these numbers. And if I look only on the first number of the triple, because the first number defines all the trip, this is what I get. They grow very, very fast. Of course, somebody has studied these numbers, but formally speaking, I have an answer to my double square perfect task. I now have a way of how to produce more and more quadratic equations, pair of quadratic equations satisfying the needed property. Well, and I was very proud of myself, of course, and thought, okay, now I understand why I couldn't find any of such equations just by trial and error. What would you do in this situation? First of all, I am a teacher by nature, which means that it's not a big mathematical achievement. I will talk about it later, but I was eager to share. I was to tell something, to share this story, and the first person to hear about it was my dear colleague Rina Tsatskis. We wrote with her, I was in sabbatical in Canada, and we wrote with her a book which all is full of stories when something that disturbed us mathematically turned out into some sort of exploration or research. Rina, of course, was very positive, but I wanted her to be my co-solver. I want us to think together, because the problem is not solved on a particular case. Well, not really. I didn't succeed to engage her to be my partner in continuing problem solving. To be fair, when she tried her mathematical story with me, my reaction was more or less the same. Interesting, amazing, please continue and tell me later. So this idea of disturbance, which constituted after all the theoretical framework of the book, also explores an idea of how difficult is to amaze somebody with something that amazes me. It's quite not a joke, because as teachers we are in this business. But another thing that I'm trying to say, that I could reflect on the story I told you in terms of so-called shifts and model of problem solving, which is inspired by John Mason, and attempts to understand, to describe successes and failures in problem solving that I mentioned in a bit more nuanced way. An idea, a pivotal idea for solving problem come as a shift of attention that can come from my personal resources and some external resources, and all this happens when I'm in position to choose. I can choose different things. I can choose what challenge to take. I can choose what schemata to use. I can choose with whom to learn. So all the idea, and you're not supposed now to really read this circle, is that my shift of attention, when I noticed this twin lead leg triple, came more or less in accordance with this model. I also can reflect on this experience in terms of productive struggle, because in a way it's the core of the essence. By classic definition, to have a problem situation within somebody who would struggle with it. So you need to put effort, and if you are lucky, you need to feel that in some way it is productive. Productiveness is associated with positive attitude toward challenges and setbacks. To illustrate this point, I found on the internet two pictures. Sir Edmund Hillary, a great son of New Zealand, with Sherpa Tenzing Norgay, are climbing to the Everest, to Jomolungma. So it is struggle, and here they feel that they were very, very productive. My attempts to share the story with the teachers led to quite interesting results. Usually the teachers appreciated the initial task, but were quite disengaged from what was the most important for me, this small exploration that I told you. But once something interesting happened. I finished the story, but no wonder that I couldn't find any examples by trial and error. And one of the participants, a teacher, his name is Anatoly, said, "Boris, what are you talking about? Please." And he immediately presented two additional examples of such equations which are not captured by the method that I developed for a particular case. Wow, no, not very weird. So something else is going on here. I used this story. He explained, how did you find it so quickly? Trial and error. What didn't work for me? Probably he solves more quadratic equations than I do during a year. When I was trying to share it with mathematicians, I used this story with as one of my mathematical encounters with Avi Berman at his 80th birthday. It was a big conference, and finished. Everything is great, and immediately after that, I received an email from Uzi Vishne. It was one of professors of mathematics who was in the audience, and he wrote me such a polite text. Immediately, I just finished my talk. I'm sitting now at Avi Berman's 80th birthday conference, where I enjoyed your talk earlier. I don't know how much thought you actually spent on the riddle concerning the mistaken coefficients, but there is something you might find useful, and of course, 3-line solution of a general case. I can share it by request, but I'm not stopping it now. It requires some parameterization of, okay, I really can share it if you wish. But to make my point, my next attempt was to share this problem with a team of the project which we call Raising the Bar in Mathematics Classroom, which is devoted to activity that can encourage school teachers to use problem-solving activity in terms of productive struggle. The project, we were a quite interesting team, I believe, very diverse team, including specialists from different directions. And we develop some activities, do PD of different formats, and try to somehow encourage problem solving in Israel in this project. Well, but people in this project are very critical, and Jason Cooper, who co-leads this project with me, said, well, I don't like this miscoping task. It is too straightforward as is, and your exploration story is too complicated to be used in middle school. So there was developed, led by Jason, but it's not individual work, it's a teamwork, another version of this task to be used in middle school. So for a while we have two versions, original and modified. I like very much original, Jason likes very much modified. We argue, we cannot convince each other, but we should not convince each other. Every time when I go to teachers, I use my version. Every time that Jason goes to teachers, goes to his version. And by the way, it happened not only with this task. As a team of designers, what we do, we find something interesting, we modify it, and turn it into materials for our PDs. But then, when we use it in our courses, it was repeatedly the same phenomenon. Much more chances that I will use with teachers a task that I was involved in designing than I will take somebody else's task. Again, the same story, the agency. How can you amaze somebody with something that does not amaze you? And here I would like to paraphrase a quotation from Jeremy Kilpatrick that I quoted earlier. Kilpatrick said, "A problem for you today may not be one for me today or for you tomorrow." Paraphrase would be, a problem of your choice may become a problem of my choice if I manage to establish a personal relationship with it, but not without these things. And of course, continuation of the story is with teachers. After all, Jason won, and his version of the problem entered the collection of the materials of the project. About 500 teachers are familiar with this collection in Israel, and quite some of them enacted the problem in a class, and 45 of them, we were lucky, we asked for this, pursued it, wrote so-called reflective reports. I will not stay for too long, but in these 45 lessons, enactment of the same problem, from the teacher perspective, we found something similar and very different. Similar is that most of the lessons included the element of teacher explanation, individual student work, and orchestration of general discussion. But individual teachers, the lessons varied greatly. Somebody put emphasis here or here or here. So we had a huge diversity of scenarios from the teacher perspective, and I felt, wow, this problem is now more alive than it was a year ago. But of course, interesting things happen. This is a quotation from teacher respondents, that they were surprised about many things around the same problem. Somebody says that I was surprised that it was too easy to my students. Somebody was surprised it was too difficult. I was surprised that they know this, they know this. But what characterizes all these open reflections that we collected is appearance to they, the students, the class. What is interesting, and this is the third challenge that I mentioned in the beginning of the talk, is to open this black box and see how this experience with the same problem looks from the student perspective. And here we needed a tool. Pictures on the screen are of Amer Badarne and Menuha Farber, members of the team, who, along with Jason and me, were involved in developing this reflective, tool. An idea was that we wanted to explore struggle and its productiveness from the student perspective. So we found the literature about struggle and identified 4 kinds of struggle. We went to some other literature and found candidates for what can count for productiveness from the student perspective. And after all this, we translated the first part, struggle, into 10 questions. The second part into additional questions. Let's just take a look. The list of questions is actually a list of difficulties according to stages of problem solving. The idea is quite simple. So one difficulty can be, at first it was difficult for me to understand the problem formulation. Would you agree or not agree? But then we ask something else. How did you overcome the difficulty, if at all? It can be not relevant, but if it is relevant, it can be by myself, with the classmates, or with the teachers. So we wanted to have this experience. Imagine a questionnaire, online questionnaire with 10 of such items, more than 10 items about productivity, which was operationalized like, am I happy about something from this lesson, solve this problem? And then we have a list of things about what can make probably students happy. Or they solved problem, or they collaborated with students, or they encouraged by teachers. We had quite a long list of some things, and of course some open items. All this is given as an online questionnaire, sometimes online, sometimes on paper questionnaire, to be filled out immediately after a problem-solving lesson for many problems in this RBMC project. It takes about 10 minutes to fill out, and it takes about hours and days after to make sense of what we have out of this questionnaire. So just a simple example, a teacher, Orna, who taught 30-year-old students, used the miscopying task with 29 students. She was quite positive about the lesson. The questionnaire revealed that the task was a problem for 23 of them, and 6 did not respond to it as a problem. More ideas is types of struggle. We could characterize types of struggle in this situation. We could characterize kinds of productiveness. 27 out of 29 students were happy at least about something. And some of them were happy about more things. Examples of what they were happy about are here. Somebody was happy that I succeeded to solve the problem. My first idea was right, I just hadn't thought so. I coped with the problem as well as I could. I understood the solution found by other students, so on and so forth. So the problem is more alive than we could imagine after 45 reports by teachers when we opened these black boxes of the classes. We see a huge amount of scenarios. What I'm trying to say, first of all, I'm almost done with defending the metaphor. Because this story, I told it in particular in order to say that miscopying task attend its life with the mediation of different people, and we can describe it a little. It is not from Adler's theorem, but the stages can be from birth. I also want to say that miscopying task is still alive, it's still in use, but its life is very fragile. We don't know what will happen tomorrow. For example, this talk can affect the future of the miscopying task depending on what you do with it. You can take it to your course or PD, but tell the solution, so it would not be a problem. This is what I did today. Or you can make your students struggle, so you will revive the task as a problem. Or you can use it for exploration, or you can just forget about it and think about Tinkerbell in this situation. My next point is that when I more and more think about different definitions of problem, I doubt if such an object exists. Task, yes, but I doubt now if a miscopying problem is a problem according to which definition. Somehow it has many different modes of living experienced by different individuals. If we come back to ways of solving it, we would say from student. Student has resources and choices, but these choices are not random. They're stipulated by teachers' choices. And teachers' choices are not random. They're stipulated, for example, for types of rationality or by types of accountability of what you want to do. All this becomes not readable and very complex. So we invented another metaphor to deal with this complexity and called it implementation chain. We can say that the miscopying task went through implementation chain. Somebody invented it having plans. It is an intended activity. Then teacher planned how she is going to use it in a class. And there are more plans than inventors of the task could imagine, so the second rectangle is larger. Then it is somehow enacted, and in most places it is not as it was planned, and experienced by students. It's very simple, and it's not entirely new. Not 4, but 3 parts appear in variation theory or in curriculum design research when we talk about enacted curriculum and so on and so forth. But for us, this metaphor invites research questions. Some of them, for example, how and why has task been designed, are questions that could be asked before this metaphor. The same, if I'll ask in terms of implementation chain what characterizes the intended versus planned uses, it would be somehow, probably you would say, very close to documentation approach to didactics. And I agree, of course. If you ask what characterizes the planned versus enacted uses of the task, somebody would say, but it is about contingency decisions, which is also explored. And if you just ask about experienced, you would say, well, here we have tons of evidence about how students solve problems in different situations. But there are some questions that we feel are refreshing for us. How do various choices made by different stakeholders affect the task implementation chain? Oh, sorry, diversity should not be there. And how these choices are negotiated? Of course, how can research along the implementation chain inform practice? And here, I'll skip several slides because what I was going to say was about another problem, but I don't have time for it. I just skip to the results and say that in one of the studies, when we obtained these huge Excel files after having responses of teachers after enactment, we asked 3 teachers to analyze the data along with us. So the teachers looked at the data, we looked at the data, and the question was, what can researchers and teachers co-learn from data on student experience with a particular task? Not surprisingly, different things. To summarize, it so happened that we looked together at the data. The teachers preferred qualitative data than analyzing Excel. We were very excited about our ability to analyze Excel files and made some quantitative conclusions. But what was the most important is that teachers were interested in results by researchers, and researchers were very much interested in results by teacher. Here I would ask you, if all this story that I tell can count as an example of how a research practice partnership can operate. Was it convincing enough to say that it is not just a problem solving, but problem solving having a flavor of research practice partnership? I am not sure. And if I ask this question, I need to ask which type of research practice partnership I am talking about. Is it a paradigm when those who create knowledge inform practice? Somebody creates knowledge and somebody uses the knowledge created. Is it a paradigm when research and practice are breached 2 ways? Research-informed practice and research-informed practice, and practice is rooted somehow in research. Or, as was envisioned in theory but rarely happens in practice, it is co-creation of knowledge. Those who create knowledge and those who use it sometimes join their forces in order to theorize something together, to make sense after these things. If we talk seriously about research practice partnerships, we always need to ask ourselves about distribution of power in such things. In this particular project that I used today as an example, there are many, many actors. It is teachers, research team, funding agency, parents, municipalities, students, so on and so forth. And analyzing, when we tried with our colleagues from Greece and the United States to analyze policy surrounding such a project, we very quickly arrived at the metaphor of policy as negotiation of power. But who has this power? And here I'd like to quote, and unfortunately I don't know who this saying belongs to, but it's very famous in science of management. The real power of a project belongs to those who can stop it. And in this way, when teachers work with me, they have more power than I do. They can do not participate, they can do not enact. And I am committed to something, and I'm trying and trying and trying. This sort of distribution of power in ideal world is supposed to be harmonic and symmetric. But if we come back to these pictures, this is not what we are right now. Research informs practice. We want to be here. Probably even more, we want to have this two-side connection between research and practice. And it would be a dream to have these co-partnerships, co-learning partnerships at scale. In our group, we experimented with several formats of how to do it. Sometimes it works, sometimes it not, and this would be a topic for another talk. Right now, let's rethink mathematics education by deciding together which mathematical problems to revive and how to reveal their secret lives. And if sometimes we feel frustrated or it looks like something impossible to achieve during our lifetime, I suggest first of all to myself to remember what I found on the wall of my room in the hotel here in Auckland. I found this saying by Sir Edmund Hillary. It's not the mountain that we conquer, but ourselves. Дякую, toda, thank you, ngamihi.
Wow, that was fantastic. Where to start? And I will try to be disciplined and make sure we have plenty of time for questions, because that was a really thought-provoking rethinking of problem solving as a teaching and learning practice for all. I think it's a very important and timely reminder of what it actually means more broadly to understand and do mathematics. I think you problematise the field really well. There are many challenges, and one I'm particularly concerned with, and it came up repeatedly, was of course the question of how to develop those problem-solving competencies and dispositions that support this sort of very rich activity. I think reimagining the tasks as organic beings that come into being as they are used and explored takes us beyond the four perspectives that you did, which are certainly part of the landscape of my own problem-solving work many years ago. And it also takes us beyond the exercise, problem, even mystery issue. And I think you've problematized very nicely, I think, rightfully, do we need this term problem? Would it be much better indeed to think about tasks that have a life? I also think that I'm being a bit indulgent, going back to my own work all those many, many years ago, I actually defined problem solving for my purposes as the totality of processes engaged in by a group or an individual in an attempt to negotiate a satisfactory solution or resolution to a situation, task or question which they actually wanted to engage with, they wanted to pursue, but for which there was no immediately available or valid solution at the outset. That sort of notion of problem solving as a process or a practice, I think is very consistent with the metaphor of problem as an organic discursive practice, and also with the notion of productive struggle. or at least what it means to struggle in the context of mathematical problem solving. However, I don't think it's particularly helpful, and you acknowledge this, in identifying, in helping teachers in their quest to create and find and choose tasks that will be experienced as problems by the majority of students in their very diverse classrooms. However, I think the researcher-practice partnership is where this comes into play and is very important. And I really like the notion of, problem solving as intended, as planned, as enacted, and particularly understanding how it's experienced by students and all the teachers in the context of messy classrooms. I think this offers a very powerful way, and I'm going to use the word birthing, and nurturing tasks to bring them into being. What I noticed was the deeply personal nature of the personal nature of the problem solving. You recounted a personal story in a very heartfelt way, and Jason's work as well was heartfelt, and the ownership of problems. There's an ownership here as well, that you embrace this life and bring it to you and want to live with it. And I think if it's a living being, it's something we not only go through modes, birthing, childhood, adolescence, and so on, but it's something we want to live with, we enjoy the company of. I also noticed the importance of recognising structure. That capacity to recognise structure enabled you to make the links, to question, to develop the wonderings. And I was interested in your account of the researcher-practice partnership in terms of the role of task designers and teachers was to revive the task, to bring it into being. And it's interesting, revive. Does that mean all tasks previously exist? Or is there a possibility for birthing completely new tasks that are yet to exist? But the main role of students was to enrich the life of the task, and I think there is a very important role for researchers to work with in that nexus with practitioners to accumulate that shared knowledge of what this actually looks like in classrooms. What I would like to know more about, I'd very much like to know more about the individual and collective resources needed, and this comes back to my original questioning, needed to enrich the life of the problem. What mathematical knowledge and dispositions are needed to make those connections, generate triggers, inspire noticings, prompt that shift of attention. We sort of know these are important, but the question comes back to how do we develop them? How do we encourage that in our students? As I'll come back to the modes of living of a mathematical task, I think that's a lovely way of thinking about this, and acknowledging too that different tasks serve different purposes and can exist for a very short time or a very long time. Some will go on and become very sophisticated beasts, and others will become quite simple, useful things that we return to. And so in thinking about a birth, a childhood, an adolescent, an adulthood, perhaps an ageing process in the life of our task, is there a life after death? I'm inclined to ask. Living organisms have parents, they engage in relationships. How far and how useful is it to stretch this metaphor? I think it's an interesting exercise. Given the intensely personal nature of problem solving, how do we then engage others in a collaborative problem-solving episode? If it's so deeply personal, how do we somehow bring other people along with us and be open enough to what they're saying to actually collectively solve a problem? I think that's what you showed was a very deeply personal, but that ownership displayed by Jason, that in a sense that can bifurcate and undo a collaborative problem-solving attempt. I really liked your quote that students have resources and choices, but they're mediated and impacted by the resources, the teachers' resources and choices. And of course that raises the whole question of power, which you dealt with, I think, very nicely and honestly, in the sense of a research practice partnership. I think of the way that you've defined it and illustrated it, I think does offer a very promising way forward for negotiating that very treacherous path in power relationships and knowledge differences and different motivations and so on. What it prompted me to think about, and this is just way out there, and there's a theory of the notion of flow. And I think that's got a lot of relevance here, and I think it really highlights that incredibly effective, role, that personally connectedness in problem solving. And in your shift and choice model, what came to mind was, and it may not be relevant at all, but it came to mind, is Burke's dramatistic pentad, which he developed in the context of trying to understand human motivations. But people and situations, but people have also used it as a means for shifting perspectives, putting yourself in someone else's shoes to try to better understand where someone else was coming from, to see new arguments and new ways of thinking about a situation, and perhaps that's something that offers something to your research practice communities. The dramatistic pentad, for those of you who want, it's B-U-R-K-E. And he talks about it's sort of like a literally an analogy or metaphor, and he talks about understanding situation in terms of there's an act, there is something going on, there's a scene, there's a context in which it occurs and where and when it occurs. But there's also an agent, and you mentioned the important notion of agency. There's an agent and there is agency, so there are both there, but there is also a purpose. Why is it being done? As I said, I thoroughly enjoyed your talk, and as I said, it brought me back over 40 years to all that work and all the people you mentioned, Lester, Schoenfeld, Vigneault, Vilma, all at that 1984 PME conference, and we had some wonderfully rich discussions about problem solving, but I am very, very grateful to have it revived and to rebirth it, and I think it's something we should have at every PME conference. Anyway, thank you very much, and now we can have some questions. So if you'd like to...